Hello and welcome to Geometry with Mr. Clausen. Today we're going to get started on the second part of our probability of banking a basket project. And what we're going to do today is we're going to look at the relative probability of banking a basket from a specific person's angular position. And with that piece of information, we're going to look at angular position, which we talked about in the first part of the video. We did some calculations with that, where if we looked at a specific angular position from the basket, what would result is that you could bank the basketball off the backboard, and the triangle that would be created from that would be a right triangle, and the angle of incidence here would be the same for both of these triangles. And then you would have another right triangle here. And what that would do is it would allow us to go and use a number of similar triangle relationships that we've talked about in previous units, and also allow us to use a whole bunch of right triangle and trigonometric relationships that we've talked about. So specifically what we'll look at today is, how do we calculate this area of the backboard that you have to aim at in order to bank the basket. And this is how we're going to try to get around some of the skill aspect that might be associated with banking a basket. Because some people, like Dwayne Wade or Tim Duncan, for example, are probably way better at banking a basket than you are. But could we still calculate relatively how much more likely they are to bank a basket at a particular position or not? And so what we're going to do is look at, instead of banking it off the backboard and making a perfect basket like we did in part one, we're going to look at the range that you have of a possibility if you bank off the backboard and land to the very left part of the hoop, and bank off the backboard and land to the very right part of the hoop. And how we're going to estimate some of this is that, if you have a basketball that lands right in the center, right, you got plenty of space, you bounce it off the backboard, it falls right in, super awesome. But if we set a very specific set of criteria for what's going to constitute this banking of this basket, we can try to come up with a theoretical model of how much more likely you are to bank a basket at 30 degrees to 60 degrees, for example. Or that's the idea that we're going to explore with this given project and see how this looks. Now, what I'm going to assume for this given project is that the diameter of a basketball, so, if we're looking at this yellow circle here that represents the diameter of a basketball landing on the rightward side of the basket, basketballs, at least, are about 9.5 inches in diameter. Now, that's not exact for every single basketball. It is a little bit of an approximation depending on what you're using. But the other thing that we talked about in the previous video is that the diameter of the basketball hoop itself is 18 inches. And so if you subtract 9.5 inches from 18 inches, what this gives me is how much leeway I have in both directions, which so happens to be 8.5 inches. Now, I'm explaining this because we need to know this in order to do the calculation that we're going to do. And once we set up the kind of premise of this whole experiment, hopefully it'll make doing all the calculations much more quick in nature. And so if this is 8.5 inches, what this is telling me is that if we take all those calculations that we did in part one of the video, so we bounce off the backboard here, all right in the middle, and then go back somewhere here, right, that our end landing spot theoretically could be 4.25 inches to the right of that position and still fall within the hoop, and 4.25 inches to the left and fall in the hoop. And now I understand it could roll around the hoop and fall in or that type of thing, but we need to set a very specific constraint in order to build the model. You start throwing in too many variables and it might not work very well. And so, or it gets way more complicated, which, we're just trying to keep a simple model here so we can build upon it maybe later, which actually is a pretty interesting thing, doing some Googling this week and seeing how much people actually look at this stuff. It's quite interesting. So if you're curious, feel free to go out and look around. But what this allows us to do is it allows us to go 4.25 inches, just as an approximation, is equal to 0.35 feet. Well, what that tells me then is that the total change in X total from part 1 of our video is either going to be 0.35 to the right or 0.35 to the left. Because the diagram that we're looking at here and all these measurements that we're looking at are in relation to the angular position beta equaling 60 degrees. So we're just continuing off where we did the 60 degree angular position in part 1. So with part 1, we went and calculated and we saw that, y2 equaled 12.99 feet. We saw that y1 equaled 1.25 feet. And if we add y2 and y1, we got y total of 14.24 feet. And x total in part 1 of the video, when we were banking in the center of the basket, was 7.5 feet. So what we're going to do in this video is we're actually going to repeat a whole bunch of calculations that we did previously, but the only thing that's going to change is X total. When we're looking at when the basketball banks on the left word part of the board into the basket and the rightward possible point of the backboard into the basket. And the thing that's really slick about all these calculations that we're going to do is that this example of 7.5 here, if we're talking about the leftward banking position of the board, this will simply be just negative 0.35 feet from 7.5. And down here, we'll just take 7.5 feet and we'll add 0.35 feet. And so if you're looking at an angular position of 30 degrees, for example, what that's going to look like is something like 13.34 feet for the rightward trajectory and 12.64 feet for the leftward bound trajectory. So when you're going through and trying to calculate some of these things, it's really going to make things a lot more simple. So if you got your original table from part 1, grab that because you're going to want to reference that when you're going through it, and maybe you can kind of fill in some of the tables as we go through this and make this a little bit more simplified process. So for example, we knew from the part 1 of the video that the X total distance was 7.5 feet. All right, and that's not the literal position, but we'll look at beta of equals 60 degrees here. And in the top part of the table, we're going to look at where ball lands left. So we'll do that first, and then I will show you again where the ball lands right, just so you can see another example. And if we have 7.5 feet, for the leftward position, we are going to subtract 0.35 feet from 7.5 feet, and this will equal 7.15 feet. Try not to let it go into this 90-degree table, but I just want to show you that it's this simple. And for all of your calculations that you're going to do, you're going to subtract 0.35 from every single X total from part 1 and put it in this column. And the beautiful thing is that the Y total column here, this 14.24, this is the same. The 12.99, this is the same. The 1.25, this is the same. And really the only thing that changes, because X total changes, well, X2 and X1 also have to change. So we do have to do that math. But if you remember previously, remember that Y total all over Y1 is equal to X2 all over X1. And if you have X1 plus X2 equals X total as your equation, that's all we need, our similar triangle relationship and our segment addition postulate relationship. And because we have all these values here that we had before. And what you should know is that Y total over Y1 equals 14.24 all over 1.25. Now, please keep in mind that this will only be true for an angular position of 60 degrees. It will change as you go to 45 and 30. You should have gotten, I think, a ratio or scale factor. That's what this is. This is your scale factor. Your scale factor for 45 degrees should have been about 9.5, 9.48, something like that. And then your scale factor for 30 should have been 7. And so if you were still a little stuck on how to do that, that's where you would go from there. But so if you have this, now we understand that, again, based on this ratio, y total over y1 equals 11.39. So that means x2 over x1 is equal to that scale factor. We multiply both sides by x1, and we would get that x2 is equal to 11.39 x1. Substitute that into our equation up here. Substitute that in our equation up here. If we rewrite that down here, what we would get again is x1 plus 11.39 x1 is equal to the x total, which, remember, in this case changed. It's now 7.15 feet. We set this equal to 12.39 x1. Divide both sides by 12.39. And what we should get is that x1 is equal to 0.58 feet. And if we want to find x2, all we need to do is subtract x1 from both sides. So you get x2 is equal to x total minus x1. And this hopefully is fairly simple and straightforward. You just have 7.15 minus 0.58, and what you should get is 6.57 feet. So you have 6.7 or 6.57 feet and 0.58 feet. All right, and so now we have some important information, but we need to do the whole thing again where the ball lands to the right. So in this case, when you're looking at this second row of your table, 7.5 feet plus 0.35 feet is equal to 7.85 feet. Just like I had shown previously here, we had the 7.85 feet. So now we're looking at the rightward trajectory of this basket. Now, all these other values, again, y total, y2, and y1, will be the same, at least as if you're staying in the same angular position. Change the angular position, all this stuff will change. But once you calculate it once, you should have most of what you need. Unless you're talking about y1. 1.25 feet is y1 because that's based off of the distance that the basket is from the backboard itself. And so now we just have to calculate x2 and x1 again. So if we go back to this relationship of y total and y1, where you have 14.24 feet divided by 1.25 feet, again, remember that this is 11.39, and this is your relationship of x2 over x1. So if you multiply both sides by x1, you get x2 equaling 11.39 x1. Plug that in for x2 over here and get x1 plus 11.39 x1 all equals x total. Let's plug in what we know and simplify. So 12.39 x1 is equal to the 7.85 feet that we have here. Voila. Now divide both sides by 12.39, and hopefully all these steps are starting to look pretty simple, or similar, I should say. And if we do this calculation, you'll find that x1 should be equal to 0.63 feet. And now if we go and subtract 7.85 and 0.63, x2 should equal 7.22 feet. So we have 7.22 feet, and we have 0.63 feet. Now, the numbers that I want you to draw attention to here is, I want to draw your attention to the 7.22 feet and the 6.57 feet. And I want you to use x2 specifically, because if we go back over here and now we look at these relative positions, you actually need to avoid using x1 because the points where x1 start here vary slightly. But the x2 starting position here is relatively consistent. So x2 for the blue line here is your 6.57 feet, and your x2 for the y position is 7.22 feet. So now if we want to find delta x, all we have to do is take the absolute value between these two numbers. So what I'm going to do in this case is, if we want to find delta x, all we need to do is take the absolute value of these two numbers, and I'll just keep it simple. I'll say x2 of the green line, which is the rightward bound position, minus x2 of the blue line, which is the leftward bound position. Now, the only reason I'm showing this to you with the absolute value bars is that, you know, if you did this the other way and got a negative number, you would still have the difference. That's what the change of actually is in this case. And so if we want to find delta x, it's pretty straightforward. Just go the 7.22 feet minus the 6.57 feet. And now delta x is simply equal to 0.65 feet. And hopefully that seems relatively straightforward. But now we can just write that down here, and we can calculate this out. And now, if you want to go calculate it for some of these other positions, you can just go and add some of these other positions. Now, I will point out just a word of caution when you're dealing with the beta of 90 degrees. Some of you probably did that and thought it was the easier calculation, and that's awesome. Once you kind of wrapped your mind around what was going on, it probably wasn't super intense. But the thing I want you to be careful about when you're looking at this specific example is that if you are the player and you're banking the basket, all right, from this position. Now, I know a basketball hoop isn't this big, just bear with me. But when you're estimating this trajectory, just keep in mind that, you know, your rightward bound basket is going to look something like this, and your leftward bound basket is going to look something like this. So it's going to look a little different as far as how you look at some of these different values and how you calculate. So what that means is that, you know, from that absolute distance from center, you know, there's a couple different ways that you can try to look at it and go through it. But I would just treat the X total for both of these circumstances, you know, in terms of the leftward bound position and the rightward bound position, as just that 0.35 feet for both of these given circumstances. And I think if you just take that into consideration, that'll make things a little bit easier as far as what you're looking at. But just make sure you're thinking that through when you're going through that, because the orientation's a little bit different. And if you got questions about that, feel free to shoot me a question or ask a peer and ask them if they got the same answer. Just keep that in mind, that looks a little bit different in comparison to the rest. Now, the last part of this video that I want to talk about here is how do we calculate the relative probability. And what I've noticed over the years, I actually had to update my form a little bit, because if you change the positions and those type of things, what actually has the highest relative probability changes slightly. So the distance that you are from the back and just some of the different distances that you look at. And if you ever just search like probability of banking a basket, you'll probably see this project on Science Buddies. But you'll also see, physics departments like going and calculating all this data out, and the NBA has all these shot charts where they'll just show you the relative probability based on like position on a court. It's actually really interesting to look at all those distributions. So if you're into basketball, go look at that. If you think basketball is boring, don't go into that. But one of the things that we're going to look at here is that when you're looking at the relative probability of banking something, the idea implies that you want to find probability P like you would in algebra. You maybe looked at this based on an angular position of beta. And typically what you do is you take the probability or the area delta x that you're looking at based on its given angular position, and then you divide it by the delta x that is the smallest out of all your calculations. And what I will tell you for this particular project is that 30 should be your smallest value that you have here. And so let me give you an example. This isn't the real value, so don't write this down in your table. But let's say, we do this and we find that the length of contact x, the smallest point that you have, let's say, is 0.05. And if that was the case, if it was 0.05 feet, that would be a relatively small position. And so the theoretical argument would be is the probability of banking an basket at 60 degrees, if it was based off of the smallest position, would look something like this, where you have the 0.65 feet and you divide that by the area of the smaller position. And if you look at this closely and you simplify it out, you will see that this equals 13. So if you put 1 for a relative probability, a theoretical probability, you're just listing out that this is the smallest number. And if that was the case, and you can put that on your table because I told you that was the smallest, at least when the angular position is the ones that we're looking at here at a distance of 15 feet. But if this was the actual number at the 30-degree angle, what this tells you is that you are 13 times more likely to bank a basket at 60 degrees than you are at 30 degrees, for example. All right? So don't use this number. I'm just explaining that. So once you get some of these other calculations, you're just taking the smallest one and you're putting all these values over the smallest one. And the reason why this is 1 is that if you look at, if this is the smallest position, right, and you go probability, and you go probability of beta, or let's say 30 degrees, and you have whatever the distance is, delta x at 30 degrees all over delta x of 30 degrees, well, this should equal 1, regardless of what delta x is. And normally I would determine this after I find all the length of the contact lines, but in this case, I'm just going to give you a little hint and tell you that's there. So with that said, I'm going to leave you to do the rest of this. You have your part 1 data, hopefully, and so all you should need to do is kind of fill out a lot of these similar parts, add and subtract these different positions based on whether the ball is landing left or right, and see if you can calculate all of this out. With that said, let's do some math.